Here are your 5 a day, and here are the answers. Let me know if you have any questions about those. So today we're going to be looking at graphing using polar coordinates and how certain graphs can be represented in polar form. So we can switch between polar and Cartesian equations of curves using these relationships that we found last lesson. Remember that the Cartesian equation of a line is the relationship between the x and the y values for points on the line, whereas a polar equation tells us the relationship between the distance from the origin and the angle from the positive x-axis. So let's have a look at some examples. Here I've got to find the Cartesian equation of the curve r equals 5. This process relies on using some of these expressions above and trying to turn this equation into one of them. For example, if I could make the equation have an r sine theta in it, then I could replace that with a y. I can't do that in this case, but what I can do is square both sides. Now I have an r squared. This relationship here has an r squared, so I can replace the r squared with x squared plus y squared. Now, this you should recognise as a circle, which has a centre at the origin and a radius of 5, which is the square root of 25. This actually makes sense. If you think about this polar equation, it just says that the distance from the origin is 5. It doesn't mention the angle. So, let's try this one. Remember, I'm aiming for something up here. Let's start by rewriting cosec theta as 1 over sine theta. Now I can multiply both sides by sine theta, and I have r sine theta. That's here and it's equal to y. So I can rewrite this, and it's the horizontal line y equals 6. So sometimes moving from a polar equation to a Cartesian equation makes things simpler. Pause the video now while you have a go at questions 2 to 6. Here are your answers. Please mark your work and let me know if you have any questions. So we can also sketch curves based on their polar equations. The polar equation r equals a, where a is some real number, is just a circle with the centre at the origin and radius a. The polar equation theta equals a, where a is some real number, is a half line starting at the origin and making an angle of theta with the x-axis. The positive x-axis. So you'll note here that I've just drawn a half line. That's because that's the only part that will have the correct angle, which is why it doesn't extend to a full line. Sometimes we can put the dotty part in. The polar equation r equals a theta is a spiral which starts at the origin. Now, this is where it starts to get a bit more complicated. This is a very simple equation, but the line is not very simple at all. Let's have a look at how we graph this. We're going to work out some points. Just like when we first learn how to draw graphs in the Cartesian plane, we pick some values for x and substitute them in to find y. Here we're going to choose some values of theta and substitute them in for r. The values of theta that we choose, we're going to choose ones on the axes to make them easier to plot. So I've gone for 0, pi on 2, pi, 3 pi on 2, 2 pi. When our theta equals 0, our r is equal to 0. When theta equals pi on 2, r is just a pi on 2, and so on. Now I don't know what a is, but it's just some number. So I can plot this on a set of axes in terms of a. The point 0, 0 is still the origin. It's a good idea to label the axes with the angles they represent, just to help you with your plotting. When my angle is pi on 2, my distance from the origin is a pi on 2. So I can plot that point there. So I know that I've defined this distance as a pi on 2. When I'm at pi, my distance from the origin is a pi. So that's going to be twice as far from the origin as this point. When I'm at 3 pi on 2, my distance from the origin is 3a pi on 2. So that's going to be 3 times the distance of this point. And when I get to 2 pi, my distance from the origin is 2a pi. So this is double this. And they join together to make a spiral. Now I didn't say to stop at 2 pi there. We could keep on going forever if we wanted to. Don't have enough time to go on forever though, so up to 2 pi for now is going to be acceptable. Now, why is it like this? As we turn through the angle increases and so will the distance. As theta increases, r is just proportional to theta, isn't it? It's just some constant times theta. So as the angle increases, the distance from the origin will increase. Let's have a look at this one. So let's draw up a table of values and consider what the value of cos is for each of these. So when theta equals 0, that's this point here. When theta is 0, cos equals 1. Or cos theta equals 1, sorry. Cos theta equals 1, this whole expression is 2a. At pi on 2, cos pi on 2 is 0. That's this point here. So I substitute 0 in for cos theta, and I get a. When theta is pi, cos is negative 1. Cos pi is negative 1. So if I substitute that into my equation, I get 0. And so on. Now what's this going to look like? Here are my axes. I've put my values of theta on them. When our angle is 0, our distance from the origin is 2a. When we move up to pi on 2, our distance is a. So it's half the distance that it was before. As I move round to pi, my distance becomes 0. As I move round to 3 pi on 2, my distance becomes a. And then at 2 pi, it gets back to 2a. I have this shape here, which is called a cardioid. Cardio relating to the heart, because this looks like kind of heart shape on its side here. So let's have a look at the graph of r equals a sec theta. Let's change this one to a Cartesian equation to see if it's simpler. This won't always make it simpler, but in this case it does. We will rewrite sec theta as 1 over cos theta. I can multiply both sides by cos theta. And you should remember that r cos theta is equal to x. So this is just the line x equals a. It's a vertical line which cuts the x-axis at a. Have a go at questions 1 and 7 now. This is what you should get for 1. And let me know if you have any questions. Thank you.